This is part 6 of the series Logarithmic, Exponential, and Other Transcendental Functions. In the last part, we ended with this table of trigonometric integrals. And what we're going to do now is we're going to do a couple of examples of some trigonometric integration. So without further delay, let's jump right into the first example. As with all the other examples in this series, I encourage you to go ahead and give this one a try, and then pick up the video when you're ready. So let's take a look at this integral. What we have here is the integral of secant squared x over tan x dx. And if you look closely here, we have a relationship, and we're going to pick a u du that gives us an appropriate response. So let's go ahead and pull up the solution. Here I picked tangent as my u, and therefore du is secant squared x. And so what we have here then would be the integral of 1 over u du. Since tangent is the u and it's on the bottom, it's 1 over u. Du is this secant squared x dx. And the integral of 1 over u du is just the standard natural log of the absolute value of u. We back substitute with our u, and the final integral is the natural log of the absolute value of tan x plus c. So this was a pretty straightforward pattern to match, not really too terribly difficult. Let's go ahead and move on to the next problem. So here we're being asked to do a definite integral, and so give this one a shot and pick up when you're done. And taking a look at this, we have the integral from 0 to pi over 4 of the square root of the quantity 1 plus tan squared x dx. Now hopefully you know your Pythagorean identities well enough that you can see that this is the same as secant squared x. And so that's going to form the root of our solution. So secant squared x is the equivalent of 1 plus tan squared x by the Pythagorean identity. And the integral from 0 to pi over 4 of the square root of secant squared x, the square root of anything squared, is itself. So the integral comes down to this piece. And we know from the table at the beginning of this video that the integral of secant x is the natural log of secant x plus tan x. And since this is a definite integral, we're evaluating from 0 to pi over 4. And this becomes secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0 plus tangent of 0. Secant of pi over 4, since secant is the same as 1 over cosine, and cosine of pi over 4 is the square root of 2 over 2, secant is the reciprocal of that, so this is the reciprocal of square root of 2 over 2. So it's 2 over the square root of 2. Tangent of pi over 4 is just 1, and that's minus this piece. The secant of 0, since this is 1 over cosine, cosine of 0 is 1. This becomes secant 0 is 1, tangent 0 is 0, so this is just the natural log of 1, and we know that that drops away to 0. So this whole thing comes down to this, the natural log of the square root of 2 plus 1, which is approximately 0.8814. So not really difficult. Just be very careful when you work through these elements that you don't make a simple mistake like here for secant with the cosine reciprocal. All right, let's move on to the next problem. In this problem, we're being asked to find the average value of the function f of x equals tan x on this interval from 0 to pi over 4. So give that a quick shot, and I'll start up in a second. All right. First thing we're going to do is to define our integrand and write down our overall integral that's going to give us this average value. So let's pull up the solution. So as you recall, the average value of a function, f of c, is equal to 1 over b minus a times the integral from a to b of f of x dx. And that would be 1 over pi over 4 minus 0 times the integral from 0 to pi, so from a to b, of tan x dx, that's our f of x. And then this simplifies, this is 1 over pi over 4, or just 4 over pi, times the integral from 0 to pi over 4 of tan x dx. And again, from our table, you know that the integral of tan x is the natural log of cosine x. And that's negative, by the way. It's the negative natural log of cosine x. I just pulled out the negative here, just for convenience sake. We're going to evaluate this from 0 to pi over 4. And that gives us the natural log of cosine of pi over 4 minus the natural log of cosine of 0. We know cosine of 0 is 1. So this is going to drop out to 0, and there we have it here. And cosine of pi over 4, just like in the last example, was square root of 2 over 2. So here we have the natural log of square root of 2 over 2 minus 0. And that's all times negative 4 over pi. Now, just in case you didn't actually get this value and calculate it out, you might be looking here on the surface. It may look like we missed a sign, but in actuality, the square root of 2 over 2 is less than 1, and the natural log of anything between 0 and 1 is a negative number. So a negative number times a negative number gives us a positive number. So this one's okay. All right, let's move on to the next topic, which is inverse functions. You may recall that you've encountered inverse functions many times in your math career leading up to this point, and we're revisiting it here because we're going to be doing some significant work with inverses as we move further along this series. So let's first start with a recollection of what inverse functions were. So remember that a function is an inverse of another function if the composite of, let's talk about f and h, if the composite of f of h of x is equal to x and h of f of x is also equal to x. That means then that f to the negative 1, or f inverse of x, is h of x. So that means that h of x is an inverse of function f. So only if these two conditions are met is h and f inverses of each other. So let's take a look at how we use that. What we're going to want to do here is determine that f and g are inverses of each other. So what you're going to want to do is you're going to do the composite f of g of x and verify that it comes out to x, and g of f of x and verify that it comes out to x. So why don't you give that a try and then start the video back up in a second. All right. So here is my solution. I said f of g of x, that gives us 2 times, wherever there's an x, I put the g of x in there. So this whole quantity is being replaced with this x, or is replacing that x. So this goes in where that x is. We cube it, minus 1. Now we work it through, and if you look very closely, this cube undoes this cube root. So this cube root goes away and the cube goes away, and what we're left with is x plus 1 over 2. And then the 2's cancel out here, and then the 1's cancel out here, and we're left with x. Then on the other side, we have g of f of x. So we start out with this function, the cube root of, wherever there's an x, we're going to put this function in. So that x is being replaced by 2x cubed minus 1. So 2x cubed minus 1 plus 1 divided by 2 divided by 2. Now we go ahead and the 1's cancel out, negative 1 plus 1, and then we rewrite it. The 2's cancel out, 2 divided by 2 is 1, and then the cube root of anything cubed is itself, and it comes out to x. So this verifies that f and g are inverses of each other. Now what we're going to do is talk about how we can determine if a particular function has an inverse function. Now, we can always take the inverse of a function, but we can't always say that that inverse is in fact a function in and of itself. So that's what we're going to investigate next. There are two conditions that have to be met in order for a function to have an inverse function. First, in order for a function to have an inverse function, it has to be one-to-one. In order for the function to be one-to-one, it has to be monotonic. One-to-one means it's monotonic. That means it's either always increasing or always decreasing on its entire domain. If the function is monotonic, then it's one-to-one, and therefore it has an inverse function. Let's go ahead and put this into practice in an example. And here we want to determine if this function has an inverse function. Now, the way we would determine this, we want to determine if this function is one-to-one. That is, if it's always increasing or always decreasing. Of course, the way we're going to do that is to use the slope of the tangent line, which is the first derivative of the function. If that first derivative is either always positive or always negative, we know that that function has to be monotonic. And so the first thing you're going to do is find the derivative of your function and determine if it has any critical numbers. If the function has no critical numbers, that is, if its first derivative is never 0 or undefined, then you know that that function has to be monotonic, and therefore it must have an inverse function. So go ahead and try that on this first one, and then pick it up in the second. All right, so I hope that you came up with the final result here. And we say that the first derivative here is 3x squared plus 1. We set that equal to 0, and we see that it's going to be, x is going to be equal to plus or minus the square root of negative 1/3. Well, clearly that has no real solutions, and so there are no critical numbers for this function. Therefore, this function is always positive and therefore monotonic. And so this function must have an inverse function. All right, let's go ahead and look at another example. So give this one a shot, and I'll come back in a second. Hopefully, you got this as your first derivative, 3x squared minus 1. Set that equal to 0, and you can see that x is equal to plus or minus the square root of 1/3. So clearly, this has real critical numbers, and therefore this function has extrema. So it's not a one-to-one function, and therefore it's not monotonic. So this function does not have an inverse function. So I hope you can see how this is working. Let's go ahead and look at one final example. So here's our next example, and we want to find the inverse function. So the first thing you're going to do is determine if this function has an inverse function, and then find it. Just go ahead and give that a shot. Now, when we take the first derivative of this function, we can see that the only critical number is where x is equal to 3/2. And the important thing to notice here is that this function is only defined where x is greater than or equal to 3/2. Because at 3/2, this function is 0. And at anything greater than 3/2, this function is defined. But anything less than 3/2, f is not defined. So we know that at this critical number, this function is 0. And so this function has to be positive for every element greater than 3/2 on its domain. So since the domain of f is 3/2 to infinity, and this function is at 0 at 3/2, and this function is always increasing because it has no critical numbers. The only critical number is at 0. So this function is always increasing on its entire domain, which of course means that the function is monotonic, and therefore it has an inverse function. To find the inverse, you swap your x's and y's, solve for y, and this is the inverse of this. Well, that'll wrap up this part, and I'll talk to you in the next video.